Alright, so today we're going to be talking about another few applications of derivatives, and today we're going to be mainly focusing on linearization and Newton's method. And so let's get started by covering linearization. And so we kind of talked about how the derivative is sort of the derivative is the slope of a function at some point, right? So if we were to find out the derivative of a function, let's just say like dy over dx, and let's say that the function is y is equal to x squared, then dy over dx is 2x. And so now we have a function that represents the slope of x squared for every point in x, right? Um, and this kind of motivates the idea of like if we're given the slope of the function, so if we have like again, let me just utilize the x squared example. So we have x squared right here, right? And for some arbitrary point, we have the slope at that point, right? Um, and so using the slope, we can find out the tangent line, right? At that point, because now we have the slope and we have a point that passes through we have a slope and we have a point, and so now we can find a line with the slope that passes through that point. And now that that idea of getting the slope at a particular point and then finding the line with that slope that passes through a point, and we kind of called that the tangent line before. That tangent line is also can be called the linear approximator or the linear approximation of the function centered at point C. So if this was some point C right here, and we found the derivative at point C, so in this case, my derivative is 2x, and so the slope at point C will be 2c, right? And I found that slope, and then I found the line, the equation of the line with slope 2c that passes through point c comma c squared. Again, I'm utilizing the example y equals x squared, right? So I found all of that, and that line that I found the equation of is the linear approximation of the function x squared at point c. And this process of finding the linear approximation is called linearization. And that's what we're going to be covering today. So linearization, let me just concretely define it. Linearization is defined as if some function f is differentiable at x equals a, then the function L of x is equal to f of a plus f prime of a times x minus a is the linearization of f at a. And so this essentially is just summarizing what I've spent the last few minutes just talking about. Notice how this L of x equation is just the same as what I said about finding the equation of the tangent line at that particular point, right? Because if you recall the point slope formula, right, where you have y minus y1 is equal to m times x minus x1, right? F of a is simply this point right here, right? So f of a would be c squared in our example. And so it's just the point slope formula with like y taken over here. And f prime of a is the derivative, right, at point A. And that would just be the slope that we would find. And then x minus a would just be x minus x1, where a is the point, right? And so that's the whole idea of linearization. And you might be wondering, like, why is this so important? Why is this like a thing that people care about? Well, sometimes the function itself that we have is very complex, right? If you have like a very complex function, like x squared is not as complex, but let's say we have like a high polynomial degree term, it can help to find the linearization of that function because at least around the points of um, around C, right, we can kind of give a good estimate of what that value is, right? So if we had like, um, let me motivate this in the other page. So let's say now we're saying like y is equal to square root of x, right? This is y equals square root of x. And let's say we had the linear approximate at some point c over here. And so it would look something like this. And I'm like being a little hand wavy here, but notice how at points close to c, like in an interval that's close to c, if we were to just like find the value um, of the linear approximate at a point close to c, that would approximately be equal to the actual value of the square root of x around c. What I'm saying is like if we had like square root of c plus like some value w, right? For small w's, that is equal to just using L of c plus w, where L is the linear approximate. But obviously, as you go like further and further away for w's, you get like a worse approximation. But linearization helps us get an equation that can approximate the more complex equation. So let's do an example of linearization. Let's find the linearization of f of x is equal to square root of 1 plus x centered at, and this idea of like approximation will also come again when you do like Taylor series and stuff like that. So to find the linearization, we need to know the derivative. So the derivative is simply 1 half square root of 1 plus x, right? So that's our derivative. Um, and then we also need to find out the value of function f at 0. So f of 0 is simply equal to the square root of 1, which is equal to 1. And then, so we can simply find out the equation of the line that passes through 0, comma 1 with slope f prime of 1, which is equal to 1 over, or f prime of 0, sorry, which is just equal to 1 half, right? And so that slope is simply equal to y minus 1 is equal to 1 half times x. And so y is equal to 1 half x plus 1. And that's our linearization of the square root of 1 plus x. And so let's say if we, well, that's the linearization of the square root of 1 plus x centered at x equals 0, right? So let's say we were to use that linearization to find out the value at x equals 1, and that would give us, so y of 1 in that case would be equal to 3 over 2. And we know that that is not equal to like the actual value of the square root of 2, but 1.5 is around, I think this is like around 1.4, right? So it's not a bad estimate, and that's the whole idea of linearization. And so that was linearization. And we'll now move on to the second thing, which is known as Newton's method. And so Newton's method is essentially a technique to find slash approximate the zeros of a function. And in fact, a lot of actually like a lot of the root finding tools out there use Newton's method to find out the root of arbitrary functions. And so this technique actually utilizes linearization. So now we'll see like a cool application of linearization. And so to motivate this, I'll first just talk about Newton's method generally, and then we'll prove the equation for Newton's method. So imagine like we have a curve that looks like this, right? And the idea with Newton's method is first we guess a point where the zero is going to be. So to reiterate, we're trying to find out where the zero where the what values of x correspond to the zeros of this function, right? And so we're gonna start off with like an initial guess. And so if our initial guess is some like x of 4, we'll say over here, or I'll call this x of 1, right? So that's our first guess. What we do is we find the linearization of that function at x of 1, and then we solve for where that linearization is going to lead to 0. So we're going to find out that, oh, okay, this linearization, once we linearize the function, that equation is 0 at this value x2, and that's our new value x2, and then we linearize this original function centered at x2. And so we're going to reinitialize our center at x2, find the new linear approximate with the new center, and then again we're going to find out where that approximate is 0, so that's going to be at x3, and then we're continually going to do that process iteratively. And the idea is, as we continually do this, we're going to get to the actual 0 eventually by finding good approximates, because what we're doing is we're finding a linear approximate of the function, and we're finding out where it's roughly 0, and we're using that new approximate value to re-estimate the equation, or re-estimate the curve. And as we keep doing this iteratively, we're going to get to a better refined position, and we're finally going to reach the 0, or we're going to reach close to the 0. So hopefully this like sort of structure and drawing did a good job of motivating how like why this method works, and like you kind of saw that as we did more and more iterations of that process, we were getting closer and closer to the actual 0 point. And so now let's find the equation for the Newton's method so that we can apply this very like numerically. So let's just say we have a guess, right? So we guessed at x, right? Some value x. Then because like what we did previously with linearization, we know that the equation of the tangent line through that point is simply y minus f of x, and we'll call that like f of xn, and then that's equal to f prime of xn times x minus xn, right? And now we have to solve for where this is 0 to get our next estimate. So we just simply set y to 0. So 0 is equal to f of xn plus f prime of xn times x minus f prime of xn times xn. And again, xn's are values where x is what we're trying to solve for. That's our next estimate. And so solving for x, we get f prime of xn times xn minus minus f of xn divided by f prime of xn is equal to x. And so in this term, the f primes cancel out, so we get xn minus f of xn divided by f prime of xn is equal to, let's call this xn plus 1. And so that is our update rule. Essentially, given some guess, and we call that like given our nth guess is xn, we now solve for our next guess, which is our xn plus 1, and that's our like new guess of where the 0 is going to be. And as you apply this update rule and you keep going and you keep as you keep applying this update rule for higher and higher numbers of n plus 1, you're going to see that this difference over here, or you're going to see that like the difference between x of n plus 1 and x of n is going to continually decrease. And at some point it's gonna get really like the difference is gonna be really small. So more concretely, x of n plus 1 minus x of n um, is going to be really small, and you'd basically stop going to the next iteration when you get like when you've gotten a value that like you're satisfied with that's very small, and when it reaches below a certain threshold. And that's the whole idea behind the Newton's method. We're using linearization, and we're using the fact that like the linear approximate of a function at some particular point is going to roughly correspond to how the actual function behaves. And so we solve for where that linear function is 0. So if this was x, what we did with this equation over here is if this was x of n, right here, if this was x of n, we solved for where we found the linear approximate, and then we solved for where that value hits 0. And we found out that value is x of n plus 1. So that was one step. And our next step to find x of n plus 2 would be to find the linear approximate of the function at centered at x of n plus 1 and solving for where that hits 0. And we'd get some value of x of n plus 2. And you notice how as we're increasing in the number of iterations, we're getting closer and closer to the actual 0 point. And that's because we're banking on the idea that the linear approximate closely resembles the shape of the function, and by traversing that path and descending on it, we're gonna reach closer and closer to the actual zeros. And so that's how we find the zeros of the function. And so, yeah, that's Newton's method and linearization. And those are two cool applications of derivatives.